Good morning, everyone. Happy Friday. Welcome to TVE Happy Math Hour, our weekly interactive math reviews for Math 1314 and Math 1324, presented by Yvette Chuca, Ruben Carizales, and Albert Isasi. Our session will be starting soon. This session will be recorded so that you may come back to it later if you need, and so others who may have missed out on today's events will be able to come and watch it. Thank you. So now, at this time, please mute your mics for the best sound experience. Otherwise, the feedback could interfere with information we will be sharing. We'll be sending the 1324 room link on the chat so that you may connect to your session if you're here for Math 1324. Ms. Della will be sending individual messages to everyone to gather your student ID numbers to sign you in. Without further ado, I'll pass it on to our presenter so that we may begin.
Good morning, everyone. I hope everyone's doing great. Thank you for joining us today for our Friday Happy Math Hour. We'll give a couple of seconds for those who are here for the Math 1324. Again, you will find the link on your chat to go into that room and go over with Mr. Alberto Isasi. Okay. All right. So, let's go ahead and get started. Yes. So today's topic, excuse me, we'll be looking at basic matrix operations and using matrix operations, right? So this involves section 8.1. So first, let's start. What is a matrix? So a matrix, the definition is a rectangular array of numbers, okay? And these numbers have a particular address, okay? So when we're looking at a matrix, the values inside the matrix, again, are located um, in an address form. So the matrix, we like to read it as a row times columns, or the number of the m rows by the number of n columns, okay? And within each row and column, again, it's the address. And this is like a little suffix here. For instance, if this would be matrix A11 refers to row 1, column 1. This is the address of this element here. Okay, so again, we can traverse down the matrix to where we go to the last element here, AMN. So it's again, M refers to the number of row, N refers to the number of column. Okay. All right. So the dimensions of the matrix, or the book sometimes mentions the size of the matrix. These both mean the same thing. This is describing the number of rows and columns a particular matrix will have. So, for instance, if we look at our first example here, um, we have a squared matrix, and a squared matrix means that we have the same number of rows and the same number of columns. So any matrix that has the same number of rows and the same number of columns is called a square matrix. So here it's a square matrix that is a 2 by 2, meaning it has 2 rows and 2 columns. Okay. This second example here, we have a 1 by 2. We have 1 row, 2 columns. Okay. And this third one, it's a 2 by 1 matrix, meaning we have 2 rows, 1 column. And then again, we have another 2 by 2 matrix. This is a square matrix again, but this matrix is also particular. When the elements inside my matrix are these 1, 0, 0, 1, this is considered or called our identity matrix. It's like our value 1. Okay, and we'll see how this identity matrix will work to solve some of our problems. All right, so first let's review the size of a matrix, or our dimensions of a matrix. So let's look at A here. Um, well, and something that I also forgot to mention, okay, that I know that I am looking at matrix, even though that maybe I have one element or several elements, okay. What's gonna determine that I'm looking at a matrix is these square brackets, okay. Anytime you see a square brackets like this, we know that we're dealing with a matrix. So for instance, we have our example A here. We have only one element, so we have one row and technically just one column. Yes, so the answer for this one would be, oops, don't have my answers here. My answer for this one would be G, right? This one right here, G, 1 by 1. Okay, let's look at B. Oh, here, let's put lines so we make sure that we know that. So A is going to be G here. Okay, this is a one by one matrix. All right, what about this B? We have um, 1, 2, 3, 4. Technically, we only have one row, but we have 4 columns. We have a 1, -3, 0, and 1/2. So this is a 1 by 4 matrix. So this one would be C here. Okay. All right. This third one here, this is also a matrix. We have 2 rows and 2 columns. This is a square matrix. So we have a 2 by 2, so that answer would be B here. Okay, and then the last example, D. So if we look at this, we have 1, 2, 3, 3 rows and 2 columns. And again, we'll always read our matrices like these. Matrices are always rows times columns. Okay, so this is a 3 by 2 matrix. So 3 by 2, this refers to D. All right. So hopefully we all know how to determine the size or dimension of a matrix. Let's see. All right. Now, what we want to do to use matrices to our advantage, okay? What we want to do is we want to convert a linear system into a matrix form, and this matrix form has a particular name, and it's called our augmented matrix form. Okay, so when we're converting a linear system to an augmented matrix, we're only going to look at the coefficients of our system. Yes. And again, we don't have to worry about the variables anymore because that's one of the beauties of matrices. They have a special value. They have a address for each point. So we know that they're in the right position, right? So for instance, if I have a linear system here, okay, which is 3x plus 5y equals to -9, and x plus 4y equals -10. Okay, to convert this into its augmented matrix form, I'm only grabbing the coefficients. So for this first one, the coefficient for the x is 3. It goes here on the first position, 1, 1, row 1, column 1. I have the 5 goes in row 1, column 2. Okay, the equal in our augmented matrix form is represented by a dashed line here. Okay. Now, also, don't be confused. This is the official way on how we write the equal sign in an augmented matrix by it's called a pipe, right? Um, when we do it on paper. But on the computer, when you see it on your WebAssign, WebAssign likes to use 3 dots. Okay, they don't use a line, but they use 3 dots. But it means the same thing. Those 3 dots are gonna represent our equal. Okay, and this is equal to -9. So it goes here. It will go on my row 1, column 3 section. Okay, and I would do the same thing for my second equation, which will represent my second line in my augmented matrix. The coefficient here for the x is just 1. The coefficient for the y is 4. It goes here on the row 2, column 2. Again, the equal is our line here and equals -10. Yes? Again, this augmented matrix is encapsulated in my square brackets. This is telling the reader that I am looking at a matrix. So this is the way we convert a linear system into its augmented matrix form. Okay. All right. So let's also work backwards. Or no, let's do it again. Write the augmented matrix of the system in linear equations. So we have a linear system, okay, and we want to convert it into its augmented matrix form, and then we have a second part. We want to know the dimensions of that augmented matrix. So again, I'm only going to be grabbing the coefficients of my variables. Again, the equal will be represented by a line. Okay, so I see that I have 1, 2, 3, 4 equations. So I should have 4 rows. Okay. So again, I'm going to form my bracket, my square bracket. I'm going to go ahead and already include my equal sign here. So the right side of the equal is our constant, which is what the equations are equal to. And then you can see here, the columns are going to be represented by our variables, the x, the y, the z, and the w. And I went ahead and put the variables on top here so that way we make sure that we put them on the correct address. We want to put it in the correct slot, because then if not, we change the equation. And we want to have the same thing, right? We want to have the the correct representation of our linear system in its augmented matrix form. All right, so let's go ahead and get started. So we will start with this row 1. Okay, so there they all went. All right, no worries. So we'll start with the row 1. We'll do it together. So my x value for my coefficient here is 1. My y value is 3. But you see, I don't have a z here. Again, this is the reason why I put the variables on up here. So since I don't have a z, the way I'm going to represent that I don't have a z in my augmented matrix form is by putting a 0 here. Okay, so then my coefficient here for my w is a -1. Okay, so I have to follow the symbol, the sign that's in front of it. So we have a -1, and again, our line is equal to 9, my constant. And I'll do the same thing for row 2. Again, I don't have an x, so it's 0, -1, 4, 2 equals -2. Okay, my row 3 or my line 3, my equation 3, right? So I have an x1. I don't have a y, so that's 0. I have a -5 for a z, -6 for a w, equals 0. And then my last line or last equation for my row, I have a 2, 4, -3. I don't have a w, so that's 0, equals 4. Okay, so this is, I converted my linear system into its augmented matrix form. Now to determine the size of my matrix or the dimensions of my matrix, I count the number of rows. I had 1, 2, 3, 4 rows. Now I need to count the number of columns. I have 1, 2, 3, 4, 5 columns. So the dimensions of the matrix is a 4 by 5 matrix. Okay. All right. Easy stuff, I hope. All right. Now let's go ahead and work backwards, right? It says write the system of linear equations represented by the augmented matrix form. So now what I want to go is from a matrix form to its linear system. So the first thing that I noticed here is that I have 2 rows. And again, we copied this from our website. If you see here, website doesn't put a line, they put 3 dots, okay? But this still means the same thing. This is the equal part, okay? All right, so I know that these values are just my coefficients. So since I have two columns to the left of my constant, right, to the left of my equal sign, that's just telling me that I only have 2 variables. And again, the computer is going to tell you that to use x and y for your variables. So because I have 2 variables, I'm going to use my variables x and y. So here, the 6 refers to the x, so it's 6x. The 5 refers to the y, so that would be 5y. Again, my dots here equals 2. Then the second row, the 3 refers to the x variable, so our coefficient, so we have 3x. We have a -9y, again, equals 0. So this is the way we can also convert from from a matrix form to its linear system. Yes. All right. So let's look at this example. Write the system of linear equations represented by the augmented matrix. Okay. All right. So here, again, we're forgetting our, let me go ahead and put it on here. We had our equal sign here, okay, for our augmented matrix form. So for this one, okay, we see that we covered this one, right? This part right here, it's our, if I would have a bracket here, would be our squared identity matrix. So what this means is the way we use our identity matrix is to tell us the value of these 2 variables, right? I said that I had only 2 columns, so I have 2 variables, my x and the y. So the fact that I have a 1, 0 here, this is giving me the value of the 4. And what I like to tell students is like, if I want to find the x-intercept, I set y equal to 0, right? So the fact that I have a 1 here is telling me the value of x. So here, my value of x is 4. If I wanted to find the y-intercept, I said x equal to 0, right? So the fact that I have a 1 here, this is telling me the value of y equals 3, okay? So this is how we use our identity matrix. Our identity matrix is going to give the solution for the variables that we're using in our matrix, okay? All right, so in order for us to solve for our variables, we have to do what's called elementary row operations, okay? And these are our three basic row operations that we'll use, and also the notation, because you'll have some homework problems that will ask you to write the elementary row operations um, that you'll be performing, yes? So the first operation is we can interchange rows, okay? We can change one row with the other. I mean, we can make one row be column 1, another one be column, swap them, right? In other words. So the notation that we use for that is we have some row A, and we're going to swap it or interchange it with row B, with another row within the system, okay? So the other operation that we can also do is we can multiply a row by a non-zero constant. Um, so here, if C is my constant, which cannot be 0, I can multiply it to that row. But again, you also want to think of matrices that they came from equations, right? So when we're multiplying this constant, we got to make sure we multiply it across the row. We always want to balance the equation. So never forget to multiply this constant on the right side of that equal sign, or the right side of that line, okay? Just to make sure that we are balancing the equation, and we're not giving a different equation. And then the third one is we can add or multiply a row by another row, okay? So we can replace a row by adding one row with another row, okay? And we'll see examples of all of these operations. So let's get to this, okay? So the example that I had shown you before, that I had this format here, the 1, 0, 0, 1, gave me the answer that x is equal to 4, y is equal to 3. Well, let me show you the row operations that we did that led to this answer. And the original equation was this one: 6x plus 5y equals 2, 3x minus 9y equals 0. So our first step, when given a system of equations, a linear system of equations, we're going to convert it or write it in its augmented matrix form, which is this: 6, 5 equals 2, 3, negative 9 equals 0. Okay, so now we're going to go ahead and do our basic um, row operations. Okay, so again, as an example of interchanging two rows, so for instance, in my original matrix here, I had the first row was 0, 1, 3, and I'm missing the equals, equals 4. And then I had row 2 was negative 1, 2, 0, 3. So what I can do is I can write row 1 interchange with row 2, okay? And by me doing that, I make row 2 now be row 1 and row 1 be row 2. So you see here, my row 2 now is in the first row, and my row 1 is now in my second row. Okay, so this is the example of interchanging two matrices. An example of multiplying a constant to a matrix. So if the notation would be, I want to multiply a 1/2 to row 1 to give me a new row 1. And again, this is the complete notation that we write. We are multiplying a constant to the row 1, and the arrow is telling us that we're going to make this our new row 1. So when I multiply a 1/2 to row 1, again, I'm going to multiply to all of the elements inside the matrix that are in row 1. So the 1/2 times 2 is going to give me the 1. The 1/2 times the negative 4, that's going to give me the negative 2. The 1/2 times 6, that's going to give me the 3. And then the 1/2 times the negative 2, that's going to give me the negative 1. Okay, so this is an example of multiplying a constant to a row in our matrix. And then the last example, how to add two rows together to get a new row. So here, the notation is, I want to add row 1 and row 3 to get a new row 3. But because again, the effort is to get the identity matrix. We want to have a 1 0 0 1 notation. So since I'm using rows 2 and row 3, I want to eliminate this 2, right? I have a 0 here already, so I want a 0 here. So I'm going to multiply a -2 to row 1, and I'm going to add it to row 3, and that's going to give me my new row 3. So again, we didn't do scratch work here, but we can do it in our heads, right? If I do -2 times 1, that's a -2. -2 plus 2, that's going to give me my 0. -2 times 2 is going to be a -4. -4 plus 1, that's that -3 that we have here. -2 times a -4, that's a positive 8. 8 plus 5 is 13. That's the value that I get here. And then the last one, -2 times 3, that's a -6. And -6 plus a -2, that's going to be a -8. So this is an example on how I can add two matrices together to get the desired outcomes and to get a new row. Okay? All right. So let's use this example to solve the matrix, since we already knew the answer for the other one. Okay. So the first thing that we need to do again is convert this linear system into its augmented matrix form. Okay. So let's go ahead and do that. So that's 2, 1, 4, -1 equals 8, 5. Okay. So again, we want to use row operations to get this. This is our goal, to have the identity matrix on the left side of our equal sign, and that's going to give us the answers for X and Y. Yes? All right. So the first thing that I want to do is, I don't have to do this, but since there's already a 1 on row 2, let's go ahead and use that example that we can swap two rows. So what I want to do is I want to swap row 1 with row 2. So by doing so, I have now this new matrix: 1 minus 1 equals 5, 2, 4 equals 8. Okay. Now, the next thing I want to do is I want to get a 0 here. So I'm going to multiply a -2 to row 1 and add that to row 2. And if you see here, the reason why I'm multiplying a -2, because when for me to add these and to get a value of 0, they have to have a value with different signs. So I can make the 1 be a -2, right? So by multiplying a -2. Okay. All right. So when I do this, um, let's do the work. Okay. Now I'm showing my work. I'm going to multiply -2 to row 1. So -2 times 1 um, and plus 2 is 0, is the one that I wanted there, right? Let's do the second one. I'm going to multiply a -2 to the -1. It's going to give me a positive 2. I'm going to add it to the 4. That's going to give me 6. That goes right there. And then the last one, I'm going to multiply a -2 to the 5. -2 times 5 is -10. -10 plus the 8 is going to be a -2, and that goes there. So by me adding the 2 times the row 1 plus row 2, this gave me a new row 2 that goes right here, 0, 6, -2. Now, one thing to keep in mind, when you're solving for these matrices, you always want to go from left to right, okay? You always want to take care of each column one at a time, but going from left to right. Um, Try not to deviate from this, because sometimes you can go in circles and you can get confused as far as solving, and you can undo something that you've done. So you always follow this process. Always go from left to right. Okay, so since I already have my column how I want it, 1, 0, now I want to deal with the second column. I want now a 0 here on the position 1, 2, and I want a 1 here on the position 2, 2, right? On my address row 1, column 2, I want the 0. Row 2, column 2, I want the 1. So let's go ahead. And what I'm going to do first is I am going to get the 1 in the row 2 position. So what I'm going to do is I'm going to multiply a 1 over 6 to row 2, and that's going to give me my new row 2. And again, what that's going to create is going to create that 1 that I want here. So let's go ahead and do this. When I multiply the 1, 6 times 0, that's going to give me my 0 here. When I multiply the 1, 6 times 6, 6 divided by 6 is going to be the 1 that I have here. And when I multiply 1, 6 times the negative 2, that's going to be negative 2 over 6, which simplifies to negative 1/3. And it goes right here. Yes? So I have now on my second row the 1 that I wanted. So now the last thing that I need is I need a 0 here. I need a 0 here in the position 1, 2. So I can see that's easy, that all I need to do is add row 2 to row 1 to get a new row 1, and that's going to give me what I want. So that's going to be the notation that I'm going to write. I'm going to write row 2 plus row 1 to get a new row 1. All right, so let's go ahead and do that. This one is fairly straightforward. We have 0 plus 1 is 1. That's my new value. 1 plus a negative 1 is 0. That goes there, my row 1. And then the negative 1/3 plus 5, again, get a common denominator, which was 3. 3 times 5 is 15. So 15 minus 1 is at 14, right? So we have 14 over 3 is our last value. So now we see that we have our left side of our equal sign. We don't have the pipe here, but we have our identity matrix. So what this is telling us is the answers. We have our x is equal to 14 over 3, and our y is equal to negative 1/3. Okay, so this is how we use basic matrix operations to solve for our systems. Okay, and again, just to recap, this is the reason why we do 2 chapters, because it's basically we're doing what we had done in chapter 7. We're using now matrices to find out where these 2 lines intersect, right? The value that these 2 equations share, and the point that these 2 equations share are these 2 points. But again, we're using now matrices to solve. All right. So let's look at this example, which is already in augmented matrix form, which is great, right? All right, so let's go ahead and get started. So the first thing that I'm going to do for this one is I want to get that 1 there in that first position of my first row. So I'm going to multiply a negative 1/3 to row 1 to get a new row 1. So let's go ahead and do that. So when we do that, negative 1/3 times a negative 3, negative 3 divided by negative 3, that's a positive 1. Negative 1/3 times 4, that's going to be a negative 4/3. The negative 1/3 times the 22, that's a negative 22 over 3. Okay, so I already have my 1 here. So now the next thing that I want is I want to have a 0 here, right? So what I'm going to do is I'm going to multiply negative 6 to row 1, and I'm going to add it to row 2 to give me my new row 2. All right, so let's go ahead and do that. A good also piece of advice or a good tip for you all, when solving these matrices, as you see here on my notation, I'm adding row 1 to row 2 to get a new row 2. I'm not doing anything to row 1. Row 1 is not getting altered. So it's a good piece of advice is always write down the rows that they're not changing, that you're not doing anything with. So in this particular one, my row 1 stays the same. So I don't forget that I'm not touching that one. That one's nothing's happening to. I'm gonna write it down. I'm gonna write the row 1. Row 1 is 1 negative 4/3 equals negative 22 over 3. But I am getting a new row 2. So let's go ahead and do that. Let's go ahead and do our operations. I'm gonna multiply negative 6 times 1. Negative 1 times negative 6 is negative 6. Negative 6 plus 6 is 0. Okay, so that goes there. Let's do it again. I'm going to multiply a negative 6 times a negative 4/3. So negative 6 divided by a negative 3, that's a positive 2. 2 times 4 is 8. And 8 minus 4 will give me the 4. So that position goes there. And then the last one, a negative 6 to the negative 22 over 3. Again, negative 6 divided by a negative 3, that's 2. 2 times 22 is 44. Add that to a negative 28, that's 16. So that goes there. Okay, so perfect. I have what I wanted. I wanted my column 1, a 1, 0. So now I want to look at row 2. Again, I want a 0 here and I want a 1 here. So let's go ahead and do that. Let's go ahead and get our 1 here by multiplying a 1/4 to row 2 to get a new row 2. Again, my row 1's not getting altered, so let's go ahead and write that in. Let's write our row 1 to make sure that we don't mistake it and think that we have to do something to it. We're not doing anything to this one right now. We are getting a new row 2. So let's go ahead and do that operation. 1/4 times 0, that's 0. So that's going to go there, my row 2, column 1. 1/4 times 4, that's 1. That goes there. Okay. 1/4 times 16, 16 divided by 4 is 4. That goes there. So perfect. We have the one that we wanted here. So our last step is we want the 0 here. And again, I'm going to use my row 2 to add it to row 1 to get my new row 1. And I'm going to do that by multiplying a 4/3 to row 2 and adding it to row 1. Okay. So again, now the one that's not getting altered is my row 2. So that one I'm going to write in. That this one I'm not doing anything to it. It's already done. 0, 1, 4. Okay. So the one that I'm getting a new row to is row 1 by doing this notation. So let's go ahead and do that. So let's go ahead and multiply. 4/3 times 0 is 0. 0 plus 1 is 1. That goes there. Let's multiply 4/3 times 1, which is 4/3. 4/3 minus 4/3, that's 0. That goes there. And then the last one, 4/3 times 4, that's 16/3, plus a negative 22/3, which is going to give us a negative 6/3. And negative 6/3 divided, negative 6 divided by 3 is a negative 2. And that's going to go there. And voila, we solved our matrix. We know that our x value is equal to negative 2 and our y value is 4. Again, this is my solution for this system matrix. This is where these two lines intersect. They intersect or they share these 2 points, right? Negative 2 and 4. All right. Again, if you have any questions, please let me know. All right. Okay, let's switch over to section 8.2. All right, so what is 8.2? 8.2 is basic matrix operations. Okay, so what does this mean? In this particular section, we're going to show you on how to determine if two matrices are equal. We're also going to add and subtract matrices together. Okay, some basic operations. Okay. All right, so first, the equal. We can determine if two matrices are equal when they have the same dimensions. They have to be the same size in order for 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 two matrices to be equal. Plus, their entries also have to be the same. Yes, for two matrices to be equal. Now, when we're adding two matrices together, you got to keep in mind, first, they have to have the same dimension for us to be able to add two matrices together. And what you're going to add is you're going to add address with address. Okay, the element in one position has to match the same position of the other matrix. And that's the reason why they have to have the same dimensions. If they're not the same size, we cannot add these two matrices together. Okay, we are also going to review scalar multiplication. What that means is we can multiply a real number, a constant, to a matrix. Okay. And then we're also going to subtract two matrices together. And again, for us to subtract two matrices together, we have to have the same dimensions. And we're going to subtract the corresponding entries in each of the matrices. So let's go ahead and get started with the examples. This is the best way to look at examples. All right, so the first, we have these two matrices. We like to label them A and B. Okay, just to review fully, my first matrix is 3 rows, 3 columns. Oh, this is a square matrix because it has the same number of rows and the same number of columns. Same thing with B. B is another square matrix, but this is a 3 by 3 matrix. Again, 3 rows, 3 columns. So first, A, let's multiply 3 times A. I want to multiply a real number, this constant 3, to my matrix. So this is a scalar multiplication. And the way I'm going to handle this is, again, the 3A is multiplying this 3 to my matrix. And I need to multiply this 3 to every element in the matrix, okay, to every single address. So the way we would do this is would be the 3 times 2, the 3 times 2 here, the 3 times 4. Again, the 3 gets multiplied to all of the elements in the matrix. So our result or our outcome is our answer simplified. We have 6, 6, 12, negative 9, 0, negative 3, 6, 3, 6. Okay, this is how we multiply a scalar value to our matrix. Okay. All right, how about B? So B says subtract, multiply, excuse me, a negative 1 to B. Okay, we didn't write the 1 there, but that's what that means. A negative B means that we're going to multiply negative 1 to that matrix. Again, it's the same concept. We need to multiply this negative 1 to our matrix B, and we need to multiply that negative 1 to every single address in our matrix, okay, to every single element. So when we do that, again, we're just changing the sign. So this becomes negative 2, 0, 0, negative 1, 4, negative 3, 1, negative 3, negative 2. Okay? All right, and then let's do last one, C. C says subtract 3a minus b. So we already did the work. 3a is this answer here, 6, 6, 12, negative 9, 0, negative 3, 6, 3, 6. Subtract it with b. Now, I didn't have to multiply that negative b, but we were just using it as an example. But now basically what I'm doing here um, is I already have the negative b, so I can add them. Okay, so we're not going to do that operation twice because it's saying b, right? So let me see how we have it here. Okay, so here, I'm glad we have an addition, right? Because even though it has a minus b, since I already did the minus b here, okay, now it becomes an addition. So please, I hope nobody's, I'm losing anybody here. So now it just becomes an addition of these two matrices. So to add two matrices, first, again, I know that I can add them because they are both of the same size or same dimension. And to do this operation, I just need to add each element with its corresponding element. For example, this 6 first, the one here, this position is row 1, column 1. I'm going to add it to the same position or element in the other matrix with this negative 2. This negative 2 is the position row 1, column 1. So that's how we will do the basic addition of matrices. So we have 6 plus a negative 2 is a 4. 6 plus 0 is 6. 12 plus 0 is 12. Okay, so each element gets added to its corresponding element on the other matrix. Okay, all right, questions? All right, very straightforward. So this is a copy of of um, of an example on your WebAssign homework. Okay, so and I also want to keep in mind something. Sometimes when we're adding the matrices, you see that you have arrows here on the side. This doesn't mean that you have to fill the matrix here. Sometimes you have to adjust these. So you can adjust the size of the resulting matrix by clicking on these arrows to either give it more columns or give it more rows. Okay, so this is how you can change that. Don't think that this is the position of the answer. Sometimes it is, but sometimes it's not. All right, so let's go ahead and do this example. So it's telling us, it's giving us two matrices, okay? It's giving us this matrix A, and let's look at its size. It's a 2 by 3 matrix, and we have another matrix B, which is a square matrix, so it's a 2 by 2 matrix, okay? So the first one, they want me to add matrix A and matrix B together, but what we just go over, we saw that these two matrices are not the same size or not the same dimensions. So hence, can I add these two matrices? Well, the answer would be no. I cannot add these two matrices because they don't have the same size or they're not the same dimensions. Okay, so the answer would be impossible. Cannot do it. Okay, all right. Um, so let's look at this examples. I always like to give these examples because some of my students sometimes like, what do I have to do? And it's just very, very straightforward. Okay, so here we have it's telling us that we have two matrices that are equal to each other. First, they are the same size. This is a square matrix 2 by 2. This is a square matrix 2 by 2. Okay, so it's telling me that these two matrices are equal to each other. Then for these two matrices to be equal to each other, then I have to have the same elements on both sides. So here I say they want me to solve for x. So this position for x is in the row 1, column 1. For this to be equal to this matrix on this side over here, this x has to also be a -3 because that's what that number is on this other side, right? It's on the 1, 1. I have a value of -3, so that's what x has to be. Ooh, what about y? Well, for these two to be equal, it has to have the same value. So the position here on the row 2, column 2, I have a 21. So this position, row 2, column 2, this y now has to be a 21, right? So the answer for this first one, the x value is -3, the y value is 21. It's that straightforward. And what we're testing you on this one is if you can tell how to determine if two matrices are equal to each other, okay? Let's look at this other example. It's a little bit more complicated, okay? So the first matrix here, we have a 2 rows, 1, 2, 3, 4 columns. Okay, so we are equaling to another matrix that is also 2 rows and 4 columns, but we'll have to apply a little bit of algebra on this one. So on this particular one, let's go ahead and solve for x. Okay, so x is in my row 1, column 3 position. So in the one that's supposed to be equal to, I have in row 1, column 3, I have a 2x plus 5. So what I need to do is solve for x by setting these two equal to each other. X is equal to the 2x plus 5, which is what that position of the other matrix was equal to. And then I would do the same thing just because it's already here simultaneously. The position in the 2, 3, I have a 5y minus 4, but that should equal to 16. So 16 should equal to this 5y minus 4. So in order for us to solve for x, we'll just do our algebra to go ahead and solve. I'm going to subtract 2x on both sides. X minus 2x is going to give me a minus x, leaving me equals to 5. Multiply by a -1 on both sides, so x is equal to -5. How about y? To solve for y, I just need to add 4 on both sides. So 16 plus 4 is 20. Divide by 5 on both sides. 20 divided by 5 is 4. So y is equal to 4. So this is the answer for x and y. On this first one, it was just straightforward matching. On the second one, I had to do a little algebra. But again, we are verifying that these two matrices are equal to each other. Again, they have to have the same size and they have to have the same value of elements inside its matrix for two matrices to be equal to each other. All right. So let's go ahead and do this one also, another copy from your homework. Solve for x, okay? And x is set up at an equation. Again, this is interpreting that x is going to be a matrix. So we have our matrix A, which is a 2 by 3 matrix. We have a matrix B, which is a 2 by 3 matrix already. Um, um, so let's go ahead and do this. Okay, so let's go ahead and multiply first 2 times A, and then we'll multiply 2 times B, and then we're going to add them together. Okay, so that's what I'm going to do to solve for this. I'm going to multiply 2 times matrix A, and I'm going to multiply 2 times matrix B, and then I'm going to add them together. So let's go ahead and do this. Again, we already covered how to multiply a scalar value to our matrix. So this 2 needs to be multiplied to every single element in the matrix, right? So we have 2 times the -3, 2 times the 2, 2 times the 3. Again, I'm going to get -6, 4, 6, -4, 0, 8. I'm going to do the same thing for the 2 times B. I'm going to get 6, 4, -10, 10, 0, 6. Again, to add these two matrices, I'm going to add address with address. -6 plus 6, 4 plus 4, 6 plus -10, -4 plus 10, 0 plus 0, 8 plus 6, which is going to give me, my answer is going to be 0, 8, -4, 6, 0, 14. Okay. And again, that's how I would plug it into my my homework, right? So again, we have another example. This one's a little bit more complicated because now they also have a multiple to the matrix B that we're trying to solve, but it's still the same process, right? So let's set it up as an equation. Okay, the equation here is 4b is equal to minus 2x minus 2a. Let's go ahead and solve for x just the same way. Let's set it up to have it identical to what we had just done on the previous example. So here I see that what they're asking me to solve for x here is just by multiplying a negative 1 to matrix A and subtracting it by 2 times B. So now I know what to do in order to solve for this matrix. Again, I'm going to set them up. And I'm going to go ahead and apply my scalar product to both. And then I'm going to add, the final thing is I'm going to add matrix A with a B, the new B, which will give me these values. 2, negative 5, 3, negative 5, 0, negative 10. Yes? Straightforward stuff, basic operations. Okay. So now that you know how to do addition and subtraction of matrices, let's go ahead and do another basic operation, which is called matrix multiplication. Okay, so matrix multiplication is a little bit more complicated. Okay, so this is a process. The process to do matrix multiplications, or before we do the matrix multiplication, is we need to verify one thing. Okay, that the number of columns of the first have to equal the number of rows of the second matrix that we're multiplying. If these two things are not equal, the number of columns is not equal to the number of rows of the second, then we cannot multiply these two matrices together. Okay. Now, another piece of information that you don't really is necessary, but it's good to know that the number of rows of the first with the number of columns of the second is the answer of the dimension of our result. Okay, and it's good to know just to make sure that you've done the multiplication right, that the product of the number of rows with the number of columns of the second gives you the size of the product of the two matrices together. All right, so let's go ahead and look at some examples really quick. Okay, so here we have made on A, we have a matrix which is one row, two columns, may be multiplied with another matrix which is two rows, one column. Okay, so what I like to do is I like to write the dimensions underneath. The dimensions of this is a 1 by 2. The dimensions of this one's a 2 by 1. So here I see that the number of columns is the same or equal to the number of rows of the second. So that what that means is that these two matrices, I can multiply them together, and the resulting matrix is going to be a 1 by 1 matrix. Okay, so let's look at the multiplication. The way you multiply matrices together is row times column. So here we have 4 times 1 is 4. And then I'm going to add it to 1 times 2. Okay, it's row times column. So each element will multiply to the element on the column and respectively. Yes, so 4 times 1 is 4, 1 times 2 is 2, and I'm going to add those two values. 4 times 1 is 4, 1 times 2 is 2, so 4 plus 2 is 6. Hence, I get my answer. It's a 1 by 1 matrix. Yes? All right, let's look at B. B, the dimensions of B is a 2 by 1. The dimensions of the dimensions of my first matrix is a 2 by 1. The dimensions of my second matrix is a 1 by 2. So the number of columns of the first is equal to the number of rows of the second. So I can multiply these together. So the way I'm going to multiply this is row times column. Okay, so I'm going to multiply 1 times 4. And then 1 times 1, okay? Then the second row, 2 times 4, and then the 2 times 1, yes? And I get 1 times 4 is 4, 1 times 1 is 1, 2 times 4 is 8, 2 times 1 is 2. And you see here, the resulting matrix was a 2 by 2. It's the number of rows of the first with the columns of the second. Yes? I got 4 more minutes. Let's see. Let's look at this one. This is a very common one. I think this will be the last example that I can make. But again, anybody remember, always remember that you can download these PowerPoint slides. So any of the 2 slides that I didn't get to are examples. You can go through them on your own. Okay. So let's do this. It says find a squared. So what this means, a squared means that I have 2 a's here. So basically what I'm multiplying is just 3, 1, negative 2 times 3, 1, negative 2. Okay. So again, I'm going to multiply this, and I can multiply these because the number of columns of the first is equal to the rows of the second, so I can multiply them. So again, matrix multiplication is row times column. Okay, so it's row. I like to do a big circle, but we put the color so you can see the addition, how they work. It's row 1 with column 1, and if you say this out loud, it actually tells you where it's supposed to go. Row 1, column 1. That's address 1 1. So here, 3 times 3 is 9. 1 times the negative 1 is going to be the negative 1. Okay, that's the position of row 1. Okay, now row 1, column 2. That's supposed to go in address 1 2. Row 1, column 2, 1 2. That's the address. So row times column, 3 times 1, 1 times 2. That's that address there. Okay, now row 2, column 1. That's address 2 1. That goes here, right? So row times column, negative 1 times 3, 2 times the negative 1. Okay, and then the last one, row 2, column 2. That's address 2 2. It goes right there, right? Negative 1 1, 2 2. Then I just add these values. So the resulting matrix, 9 minus 1 is 8, 3 plus 2 is 5, negative 3 minus 2 is a negative 5, negative 1 plus 4 is 3. Yes? So this is how we do matrix multiplication. Okay? Now, again, I had just 2 more slides. It's just multiplying BA. Again, I'm just going to show them to you really quick, but this was the last one. Okay. Actually, I can finish it. I didn't think I was going to finish it. So if you see here, they are asking me to multiply B times A. B is a 2 by 2 matrix. A is a 3 by 2 matrix. Since these two are not equal, the number of columns is not equal to the number of rows, and I cannot multiply. But if they had to ask me, do A and B, think about it. Could I have multiplied them? You decide. All right. Thank you all for joining me today. I wish you the best of luck in your classes and hope to see you again next Friday. Thank you all for joining me.
Thank you, Mr. Carizales, for your presentation. If anybody would like to download a copy of the presentation, you can go to the top right corner and click on the box with the arrow going down while the presentation is on the screen. We do want to remind you all about the previously recorded sessions, which are available on a YouTube playlist. This session will also be available on that playlist later today. Also linked is a short survey to help us improve our TVE sessions. Please take a few minutes to fill out that survey. And before you all leave, I want to share the TVE sessions that we will have next week. Okay, so at 1 p.m. today, we will have journaling. Okay, so at 1 p.m. today, we will have journaling for mental health with Tony Prosel. And join us again next week at 11 a.m. for Happy Math Hour, where Math 1314 will be covering inverses and determinants of matrices. And Math 1324 will be covering basic concepts of probability, permutations, and combinations. That 1 p.m. session will be a presentation by Service Learning. Thank you all for coming in today. We hope you all have a lovely weekend. And if you have any questions, feel free to use the chat box or your mic. We hope to see everyone again for Happy Math Hour.